Okay. Good evening. So I'm Mansi Tripathi. I am TA for this particular course, Environmental Chemistry. I'll share my screen, then we'll start the session. I hope it's visible. So this is Environmental Chemistry, the course being offered by NPTEL. So this is the first week of the problem solving session. As I told, my name is Mansi Tripathi. I am an IIT Madras research scholar. So we are going to do in this course is in this problem solving session. Will first there will be a little bit of recap whatever sir has taught in this whole week. After that there will be few questions which are quite relevant to the examination as well as assignment questions. So these questions will help you in solving assignment as well as examination problems. So going to the first slide. So this is what was the week one about? It was fundamentals of equilibrium. I'll try to annotate. Okay, so the first part was fundamental of equilibrium and kinetics. As we know that equilibrium is how far the reaction can go and kinetics is how fast the reaction can go. Then we discussed about equilibrium, which based on process feasibility. So in this we discussed about Gibbs free energy, that too in standard and non-standard conditions. So two conditions were there, and then we discussed about the phase equilibrium. So this was what was taught in first week. So coming to maybe the first lecture, or not first, we can say second lecture, we understood what are chemical processes. So what are chemical process? There is change in chemical bond. Some bonds will be broken and some new bonds will be formed. So wherever there is change in the new type of bond, either it is formed or it is broken, the process is called chemical process. And as I said earlier, equilibrium is how far the reaction is going. So it defines the state of the system. For example, if this is some state like if let's say SR is represented, I will represent it with G, and this is X, means the extent of reaction. So if some point is here and some point is here, so we can say what is the extent of reaction, how far the reaction has gone from point 1 to point 2. Okay, so here we can see that there is change in energy also. It means the energy has reduced here from going from point 1 to point 2. So this is what we call equilibrium. So there will be some point in between these 2 points that the system might have reached equilibrium. And kinetics is how fast the reaction is going. So if in the x-axis we take it as time, so it can define how fast the reaction has gone, the time. So from point 1, if it is going to point 2, how much time it has taken. It can be in milliseconds for a very spontaneous reaction, and it can be in days also, like for some biological reactions. So, and these are if we should know if the equilibrium or the reaction is equilibrium control, or it is kinetic control, or it is mixed control. So this is what we understood in the session. Coming to equilibrium. So what is equilibrium? In equilibrium, we say that there is no change with respect to time. Something, if some reaction is reaching equilibrium, then with respect to time there will be no change. So that is this is what we call steady state. So when something is reaching steady state, there is no change with time. For example, let's say I have some compound. Let's say I have let's say I have some antibiotic. Antibiotic is there and it is killing, and I want to remove the antibiotic from the system. So what will happen? Initially, let's say concentration of antibiotic was 1 milligram per liter. And I am putting some chemical in this. Let's say I have antibiotic in this container. And I am putting some chemical in this to reduce the content of antibiotic. So what will happen with time? The antibiotic concentration will reduce, and there will be one time after this, if after that point it is not going to reduce further. Okay, so this is just a time. This is time. So with increasing time, the concentration of that particular compound is decreasing. Okay, so from this point to, let's say, this point, it is in non-steady condition because the concentration is continuously decreasing. But after a particular point to the end of experiment, there is no change in the concentration. So here we can say that the compound or the reaction has reached steady state. So this is what we call steady state, where there is no change with respect to time. And what is equilibrium? In equilibrium, we know that how far the reaction has gone. So here in this problem, at the end of the experiment, the equilibrium state and the steady state has reached simultaneously. Okay. Here this point is equilibrium point also because the reaction cannot go further. There cannot be further decrease in the concentration of that particular compound. So it means that the equilibrium is reached. In the case of equilibrium, we studied about Gibbs free energy. So we studied this equation, delta G is equal to delta H minus T delta S. So this delta G is change in Gibbs free energy. Okay, and Gibbs free energy we know is a state variable. State variable means if Gibbs free energy of some solution or some reaction was G1 here, and then Gibbs free energy of some the same reaction is G2. So here the Gibbs free energy depends upon these points only, one point and the second point. It does not depend upon how much time it took from here to, like, if for the same reaction, if it is taking 5 minutes, for other reaction it is taking 10 minutes, it does not mean that the Gibbs free energy will change because it is a state variable. It does not depend upon any other thing. It just depends upon that particular work. So Gibbs free energy is a state function. Secondly, this delta H represents what? It is enthalpy, and delta S is entropy. Delta H will be represented by heat energy also. Enthalpy or change in heat energy or any type of energy. Mostly in case of reactions, it will be heat energy. If we talk about some physics work, then it can be potential energy, kinetic energy. Ultimately, everything is heat energy. and where delta S is entropy, that is degree of disorder. So when delta G is less than 0, we say that the reaction is feasible. How it is feasible? Some compound is going from G1 to G2. If the Gibbs free energy of G1 was 5, of G2 it's 2, so 2 minus 5 is what? Minus 3. So it is less than 0. So Gibbs free energy when it is less than 0, it reaction are feasible. Actually, everything in the world wants to go to some stable state, some lower energy state. If the energy is very high, all the, like, if we say, let's talk about asteroid and everything, they all want to go to lesser energy state. So everything in the world in terms of energy wants to go from G1 to G2. So that is called feasibility. So if the Gibbs free energy is negative, the reaction is feasible. And if the Gibbs free energy is greater than 0, reaction is not feasible. And if it is equal to 0, then we say the reaction has reached equilibrium. So that is the far most point the reaction can go. Same kind of notion is followed for enthalpy also. In enthalpy also, if delta H is less than 0, the reaction is feasible, means energy or the heat energy is reducing. So what happens? Like if we are mixing acid into water, heat energy goes out, right? The temperature increases. So it means that whatever the compound is there inside, it is uh, uh, removing the heat energy from its system. That's why the outside temperature is increasing. It is not consuming energy, it is removing energy. So energy is being reduced. So what is happening? Energy from one point E is moving down to other point. So whenever there is change in temperature, the change in temperature in the sense of increase in temperature, it corresponds to decrease in energy. Okay, so that is why exothermic reactions are favorable and endothermic reactions are not favorable. So same goes with enthalpy. And what about entropy? Entropy is just opposite. If the entropy change in entropy is greater than 0, then it is called feasible. Okay, so this is how it works. And how to calculate Gibbs free energy of a mix of a reaction? Gibbs free energy of a product minus Gibbs free energy of reactant. Actually, this is change in Gibbs free energy. Change in Gibbs free energy of product minus change in Gibbs free energy of reactant. So this is how we can calculate the Gibbs free energy of a system or a reaction. So if this thing is negative, that means reaction is what do we say, feasible in the form in which it is written. Okay, means the change of reactant to product. Like for example, reactant is going and forming product. So if Gibbs free energy is less than 0, means surely all the reactant will go and form product. Okay, but in some other reaction like A is changing to B, and if Gibbs free energy is greater than 0, then A to B, A to C is not possible. A to C is not possible. However, C to A is possible. Okay, in this case, C to A will be possible. Okay, if the Gibbs free energy is greater than 0. So Gibbs free energy, when if I write reaction from, if from A I write reaction from A to C, Gibbs free energy is greater than 0, means the reaction is not possible. But if I reverse the reaction, the sign of the Gibbs free energy will change, right? Gibbs free energy will become less than 0 again. So that is why reaction from C to A will be possible. So if we reverse the reaction, the sign of Gibbs free energy will also get changed. So all these things that we studied earlier was in standard condition. Even those are followed in non-standard condition. So what are standard condition that we should know first? So standard condition will be when temperature is equal to 25 degrees, pressure is 1 bar, and the concentration, or let's say activity, okay, activity, let's say activity is equal to 1. So there is difference between activity and concentration. Activity is represented by this curly bracket and concentration is represented like this. So what is the major difference between activity, and when activity is equal to 1, okay, then the concentration and activity are equal. Okay, so what is difference between activity and concentration? There is difference between other ionic strength. If the solution is very dilute, okay, if you take some very less amount of sodium chloride and mix it in a huge volume of water, the solution will be very dilute. In that case, activity and concentration will be similar. But if you take high amount of sodium chloride and dissolve it into less water, this activity and concentration will be different. Okay, so this will be taught later. For now, just remember that these are the standard conditions. So if there is any change in the standard condition, the Gibbs free energy formula will change. So it involves reaction quotient, equilibrium quotient, and we have also studied the relationship between Q and Gibbs free energy, QK and Gibbs free energy. So this is all we have studied. So as I told, activity is represented by curly bracket. Okay, and activity is equal to, okay, these are the things. And how we means the concentration in the current form divided by C in the standard condition. Standard condition was what? Temperature, pressure, okay, and activity. So this will how the activity will be defined. How the standard concentration is defined? Either in the molar concentration or mole fraction or partial fraction or and solid solutions are also defined by mole fraction. So when we talk about aqueous solution, it is defined by molar concentration. When we talk about aqueous solution, means anything which is dissolved in water. Okay, that is important. When we say aqueous solution, aqua means water. So anything that is dissolved in water. If you are dissolving something in methanol, then it will be a liquid solution. So apart from water, if any other things are being used for dissolving, so that is called liquid solution, because that will be in liquid form. Gaseous solution, air is a mixture of gases like that. So air is a gaseous solution. So here it is measured by partial fraction, and here the concept of Henry's law will come. Okay. So activity of the coefficient, and this whole thing is activity. Okay, and this sign is called coefficient of activity. Okay, this depends upon the ionic strength. If the solution is very dilute, then okay, then activity will be equal to concentration. If not, then activity will be lesser than concentration. So what was the non-standard condition? As we have discussed, temperature is not equal to 25 degrees and pressure is not equal to 1 bar. For temperature, we need to understand Van 't Hoff equation to determine other parameters. Van 't Hoff Arrhenius equation. So it will be something in the form of any coefficient, anything. K at theta temperature is equal to K temperature at standard multiplied by some quotient, and here also some power, in power something else, minus whatever standard condition is there. So something like this is Van 't Hoff Arrhenius equation is there. So this you will find in all the biological equipments, experiments, and any other thing. Next, we studied about phase equilibrium. So there can be different phases. If the phase can be gas liquid, liquid liquid, or fluid or solid. So when like in fluid, let's say in water, some compounds are there. And if I am putting some solid block here, these compounds can come and stick on the surface of this solid block. This process is called adsorption. And the equilibrium in these processes is explained by different kind of isotherm. So isotherm can be linear, Langmuir, or Freundlich, because here fluid and solid are exchanging some particles. Here there is some relationship between fluid and solid. So what is happening? Small particles are leaving fluid and coming and attaching on the solid surface. So this process is called adsorption. And because of this interaction, there will be a formation of an equilibrium between the compounds which is coming and sitting on the surface and which is already there, which it is coming out of the surface. It's not like that all the particle will come and sit on the surface. If some particle is sticking, some particle will go out also. So it is in two direction. So this is called solid liquid fluid solid phase equilibrium, and this process is called adsorption. Okay, and it can be of three different types, or there are more processes also. One I can remember is BET, Bunet, Emmet, and Teller isotherm. So there can be multiple types of isotherm. Okay, it can follow any of these law in law of equilibrium. Next is liquid-liquid equilibrium. So here one example is if I am mixing water and methanol. So if I mix water, let's say H2O, and I am mixing some other immiscible substance like alcohol, methanol, I'll represent it with MeOH. So the interaction between these will form a liquid-liquid phase equilibrium. So because these two liquids can be easily mixed with each other, they are called hydrophilic. And like oil and water, if we say oil and water, So they cannot be mixed with each other. So water will be called hydrophobic because it is not mixing with each other, mixing with water. Okay. Apart from that, what happened? One is there is a concept of octanol water coefficient. So I am mixing octanol, which is a kind of uh, uh, organic compound, and water. Octanol and water I am mixing. And let's say there is some compound. Let's say MEOH, methanol. Let's take a simple example, oil. Okay, there is a mixture of octanol and water. Okay, and I am putting oil in the mixture and I am shaking them properly, mixing them very well for 1 hour. I am mixing it. Then, if I'll check, the oil will be dissolved in octanol. It will not be dissolved in water. Then I can say, okay, because oil is being dissolved in octanol, oil is a hydrophobic compound. Okay, but if some compound is there that is dissolved in water instead of octanol, we will call hydrophilic compound. So this is the liquid-liquid phase equilibrium. Next concept is gas and liquid phase equilibrium. So here for dilute systems, if the system is dilute, means very less solute is there in large amount of solvent, we follow Henry's law. However, if the system is non-dilute, okay, the system is concentrated, we follow Raoult's law. These are basically same law. So Raoult's law is equal to Henry's law at very, very dilute condition. Okay. So after all this revision, this will be our first question. Now you can see the question on the board and you can answer the question in the chat box. Okay. So you can answer all these questions in the chat box. Okay. So this is the first question. So in Deepika, could you please Deepika, please turn off your mic. Yeah, I have muted Deepika. So in environmental chemistry, one of the major concept is the conversion of one compound. Just a second. Okay. So then in environmental chemistry concept, it is important to convert one unit of measurement to another because sometimes when we talk about these compounds like CaSO4, MgSO4, we may deal with them in milligram per liter concentration. Okay, but when we talk about the compounds which are found very less in the environment, like say iron, zinc. Okay, let's say we talk about these compounds in our body, then we will deal with very smaller unit of measurement like microgram per liter. So the conversion from microgram per liter to milligram per liter, all those things are very important. Apart from that, similarly, if we want to uh, compare two different units, so there should be a common link between them. So that common link is equivalent unit. Okay, we can convert MgSO4 to CaCO3 using equivalent unit and vice versa. So for to compare two different units, equivalent units are very important. So conversion of milligram per liter to equivalent unit is very relevant to environmental chemistry. Okay, so this question says the same. So in this question, convert the given concentration to equivalent unit. CaSO4, MgSO4, CaCO3. So you can solve this question and you can answer in the chat box. I will show answer also, but it will be good if you can solve this with me. Please try to solve this question. I will give you some couple of minutes. These questions are very simple. Okay, we'll see the answers now. So we know that CaSO4 was 136 milligram per liter. So that goes into numerator. And all the like for CaSO4, we know that the molar mass of Ca calcium is 40. For sulfur, it is 32, and 4 into 16 units of oxygen. And this whole thing will be divided by 2. Why 2? Because in the reactions, what happens? CaSO4 is there. Under equilibrium, what happens? Ca2 plus SO4. So here, 2 electrons are exchanged. So that is why we are dividing it by 2. If some aluminium salt is there, aluminum hydroxide and anything, then we could have divided it by 3. Similarly, for MgSO4, 24 is for magnesium, 32 sulfur, and 4 into oxygen. For calcium carbonate, 40 plus 12 plus 3 into 16 divided by 2. So, solving all this, we get 248. So, the correct option is option number C. Please note it down so that we can move forward to the next question. Coming to the next question. Now convert the given concentration into molar units, that is in the form of millimoles respectively. So we need to convert all of them into molar units now. Similar kind of question is there, conversion of between units. We'll see the solution now. So molar unit is number of moles divided by liter. So here they have not given any liter and all, so we will assume it as 1 liter, and we just have to find out number of moles. What is number of moles? Number of moles is weight of the substance. Okay, like in case of CaSO4, divided by molecular weight. So these are the molecular weight. 40 plus 32 for sulfur, 4 into oxygen. So these are molecular weight. Just dividing it by molecular weight, we will get milliequivalents. Okay, no, it's not milliequivalent, it will be millimole. This word is wrong, so this will be moles in all the places. So please note this down. We'll move forward to the next one. Moving towards next question, we need to select the correct option. The first option is all steady state processes are at equilibrium. All equilibrium processes are at steady state. Equilibrium is defined only for closed system, or steady state is defined only for closed system. So what can be correct option in all of them? Please think about this and you can answer in the chat box. Okay. Other people? Oh, we'll see the solution. So the correct option is option C, as you told. The equilibrium is defined only for closed systems. The next question is, benzene is dissolved in water to form solution of 1 liter with a concentration of 55.6 moles per liter. The initial concentration of benzene in pure organic liquid is 800 milligram per liter. Calculate mole fraction for the benzene in the given solution. Four options are there. Here it will be 10 raised to power minus 4. Okay, it is not minus 4, it is raised to power. This mistake is there. So find out solution for this question. We need to find the mole fraction of benzene in the given solution. We know the concentration in this solution is 55.6 mole per liter, and the initial concentration of benzene in pure organic liquid is 800 milligrams per liter. So using these two information, you can find out the mole fraction for benzene in the given solution. Try to solve this question. Please try to solve this question. Benzene is dissolved in water to form solution of 1 liter with a concentration of 55.6 moles per liter. The initial concentration of benzene in pure organic liquid is 800 milligram per liter. Calculate mole fraction for benzene in the given solution. Try to solve this question. You can take 2 more minutes, then I will show you the solution. Okay, we'll see the solution now. Mole fraction of benzene is equal to moles of benzene divided by total mass of solution. Okay, so the initial concentration of benzene in the pure organic liquid form is 800 milligrams per liter. Okay, so what we are doing, we are using this 800 initial concentration, and we are putting in this water. Okay, to form a solution of 1 liter with the concentration of 55.6 moles per liter. So moles of, how do we calculate moles of benzene? Mm, As we told earlier, mass divided by molar mass. So similar thing we did. 800 was the mass divided by molecular mass. Benzene is what? C6H6, right? This is the formula of benzene. So carbon 12 into 6 plus hydrogen into 6. Okay, and this we are dividing to make it liter, multiplying to make it liter, and divided by 55.6. So this was the total moles in the solution. Mole fraction is moles of benzene divided by total moles in the solution. So this is how we will get mole fraction of benzene in that particular solution. So this will be 10 raised to power minus 4. Okay, please note this down. So we'll move forward to the next one. So moles of benzene added. So actually basically what was happening, let's say there were two solutions. One was some liquid and other was some pure organic solution. Okay, so the concentration of this solution was 800 milligrams per liter. So what was happening? They were adding this to this. Okay, so when it was adding, so initial concentration was 800, and when everything was dissolved, the concentration became 55 moles per liter after addition. So initially it was 0, then we added 800, then it became 55.6 moles per liter. So look at the units. We added milligram per liter and it was converted, it became mole per liter. So this conversion is very important. So we got to know the mole fraction using that. Okay, please note this down. We'll move forward to the next one. Moving towards next question. Calculate Gibbs free energy change for the given reaction. FeO in the solid form, it is being oxidized and it is forming ferric oxide. Okay, So these are the given data. Please find Gibbs free energy change for the reaction. What was the formula? Product minus reactant. And check if the reaction is feasible or not. Please solve this one. Okay. Other people? Yeah. Other people? I'll give 1 more minute, then we'll see the solution. Even if you don't want to say the answer, solve it for yourself. Okay. Remember, it will be product minus reactant. So check if you are doing it correct. Both of you have given the same number, but the signs are opposite. So please check if it is product minus reactant. And see the sign, the moles of FeO, it is 2. So you have to multiply by 2 also. Okay, it is 2 FeO. So whatever the Gibbs free energy of FeO, that is minus 251.1, you have to multiply by 2 also. Then subtract or add. Okay, we'll see the answer. So the correct answer is option C, because my product minus reactant. So what was for the product? Minus 742.7. Okay, so this is minus 742.7, and then we will subtract the reactant, and it is 2 into minus 251.1. Okay, and for element it is taken at 0 standard condition, so that is why it is 0. Then the answer will be in minus. Okay, so the correct option is option C. Please note this down. So if sign is negative, then means reaction is feasible. Okay. Moving towards next question. Comment on the feasibility of the reaction. HCl means sodium hypochlorite is dissolved in water and we are getting H3O plus and hypochlorite ion. And we have equilibrium constant and the activities of all these compounds. So let me know if the reaction is feasible, not feasible, or it is at equilibrium, or products are converted to reactant, it means not feasible. Okay, so let me know which of them is correct. We have the equilibrium constant, you can calculate reaction quotient. Based on that, you can say if the reaction is feasible or not feasible or at equilibrium. Option D is basically option B. So you have three options only, which narrowed it down. A, B, C. Solve this one. Try to solve this one. Okay, we'll see the solution now. So we need to convert the reaction quotient as I told you. So that will be multiplication of activities of product divided multiplication of activities of reactant. So simple, H3O plus multiplied by OCl minus divided by HCl into H2O. For H2O it will be 0, it will be 1. Okay, H3O plus is 10 raised to minus 7, 10 raised to minus 4 multiplied by divided by 10 raised to power minus 3, and we got 10 raised to power minus 8. Now it is less than, as you can see, reaction quotient, equilibrium constant. So when Q is less than K, what happened? Means the reaction to reach equilibrium, we need more, to reach equilibrium, more product can be required. Means the reaction can go in this direction. It can increase. Means more reactant can be converted to product, right? To match this value, to make it equal, more reactants needed to be converted to product. When more reactant can be converted to product, that means reaction is feasible. Okay. In the opposite case, what happens? The reaction will go in reverse direction. Means product will be converted to reactant. So just remember, when Q is less than K, the reaction is feasible. Please note this down. We'll move forward. So the option A is correct. Okay. Okay. For the next question, select the correct option. Delta G is state variable. Delta H is inversely proportional to delta G. Delta S is directly proportional to delta G. If the number of moles of product is more than reactant, degree of disorder decreases. So one of them is correct. Which one that can be? This is a simple question. Okay. So your answer is correct. Delta G is a state variable. That is option A is correct. Okay. So as I explained earlier, delta G is equal to delta H minus T delta S. So from this equation, if delta H is increasing, what will happen? Delta G will also increase. So this is a direct relationship, not inverse. Okay. And if delta S is increasing, delta G decreases. So this is inverse relationship. Okay. So these two statements are just opposite. Okay. And if the number of moles of product is more than reactant, degree of disorder increases. Okay. If product are more than reactant, then disorder always increases. Okay. Please note this down. So this is the next question. Analysis of the water gave concentration of sodium calcium chloride bicarbonate of 9, 21, 6, 45 milligrams per liter respectively. Calculate the ionic strength of water sample. We have the molecular weight and we know the empirical formula also of ionic strength. I is equal to 0.5 summation of mi z square I. So this I is ionic strength, m is molality of the component, z is ionic charge on the component. So what can be the correct answer for this one? So this is not minus 3, it will be raised to power minus 3. Okay, please note this down. Please solve this question. This is one interesting. Please note down the question and try to solve this. We'll see solution in a couple of minutes. Okay, we'll see the solution. So we need to calculate mi zi square. So first of all, we need mi. All these concentrations are given in milligram per liter. So we need to convert them into molar component. Okay, we need to convert the molality. So that will be obviously mass upon molar mass or molecular weight, weight upon molecular weight. So this one is the weight. And what about sodium? Molecular weight is 23. And since it is given in milligram per liter, so we also wrote it in divided by 1000 so that we can get it in milligram per liter. It should be in gram if we do not want to divide it by 1000. So molecular weight should be given in gram. Okay, since this thing is in milligram, we are dividing it by 1000. So this is what we got. For sodium, for calcium, it's 40. For chloride, it's 35.45. And for hydrogen carbonate, it is 61. How? Hydrogen we have 1. For carbon, we have 12. For oxygen, we have 16 into 3. So 3 into 16 is 48. 48 plus 12 is 60. Plus 1 will be total 61. So We are dividing molecular weight that we got as 45 divided by the molecular weight is 61, and 45 is the weight that we have. So like this, we can convert it into molar concentration. So please note it down. And how is this Zi calculated? It is the charge on over that. So for sodium we have 1, calcium we have 2, fluoride we have -1, and bicarbonate we have -1. So like that we have all the charge. So ideally it should be, for sodium it should be plus, calcium it should be +2. Okay, for chloride it should be -1, and for bicarbonate it should be -1. However, it won't matter because we are squaring it, so the charges will be neutralized. So this is just 1 plus 4 plus 1 and -1. Now we are just multiplying this molar concentration with the square of charges. Summing it up, we will get the 1 part of ionic strength. Now we are multiplying it by 0.5 and we will get the ionic strength. Please note this down. So this is just one formula of ionic strength. There can be many depending upon the situation, depending upon the total molar concentration that you have. So this is the most common one. So this is next question. This is about gas equilibrium, gas dissolved in gas. And also we have values for hydrophobic compounds or hydrophilic compounds, means liquid dissolved in liquid. So you need to select the incorrect options. Henry's law is applicable to dilute liquid gas interaction. Raoult's law applies to non-dilute solid liquid interaction. For hydrophilic compounds, KO naught value or KOW value is lower, and for hydrophobic, KOW is higher. Higher, lower means you can say greater than or less than 1. What can be answer of this question? Okay. We need to select the incorrect option here. You see the solution? So the correct option means the incorrect option is option B. Raoult's law applied to non-dilute liquid gas interaction. So non-dilute is fine. Raoult's law is applied to non-dilute system, that is fine. But the interaction is gas-gas interaction. Okay, not liquid gas. Okay. And there are some gases which can be compressed and converted to liquid. There also this law is applicable. Okay, no, it was solid liquid interaction, right? So it is not applied to solid system. It is applied to liquid system, and some gases they can be compressed and converted to liquid, and in that case, both Henry's and Raoult's law can be applied. Okay, but it cannot be applied to solid system. For solid system, what was the effect? That was adsorption for the solid one. Moving towards next question. This is a big question. A small amount of energy available in methanogenic process forces the microorganisms involved in a very efficient cooperation. In many cases, neither partner can operate without the other. So there is this thing called anaerobic process. Here, acidogenic bacteria means the bacteria which can generate acid, and methanogenic bacteria means the bacteria which can generate methane. They live in a harmony. So sometimes what happens due to more acid, uh, because this methanogenic bacteria cannot survive in low pH, they may die off. Okay, so but for methane to produce, this acidic system is also required. But there is certain pH level below which this happens. So these are the reactions. For reaction strain S, it is acidogen, means it is generating acetic acid or acid environment, and this is methanogen. It is generating methane. So such cooperation where they live together in harmony is called syntropic relationship. So this is a typical example. A typical example is methanobacillus, which is a co-culture of two partner organisms, strain S and strain M. Okay, these two strain cooperate in the conversion of ethanol to acetate and methane by interspecies hydrogen transfer. So hydrogen transfer is happening. So if this strain S converts more acid, okay, if it forms more acidic environment, then methanogens can die also. So there should be a proper conversion of hydrogen. There should be no hydrogen accumulation. Because what is acidic environment? There will be more hydrogen atom accumulation. Then the pH will reduce, right? So we don't want that. However, how much uh, H plus this strain S is producing, that should be used by the strain MOH. If there is anything in excess, this strain MOH is going to die. So their relationship is based on interspecies hydrogen transfer. So please note this down, then we'll see the question. This is the scenario that has been given. This is a biological reaction, but it still involves a lot of chemistry. Please note this down. We'll move forward and see the question. So the critical point in this syntropic cooperation is that the reaction that strain S is catalyzing, that is equation was, is only exergonic, means the delta G value is negative, means it is feasible. So if the H2 partial pressure in the aqueous phase is low enough, hence strain MH must remove hydrogen efficiently from the solution. Okay, so first reaction is uh, feasible. Okay, so the strain MOH means the second reaction. As I told you, it should remove hydrogen efficiently. Otherwise, there will be accumulation of hydrogen in the system. And if that happens, the pH will reduce below a certain threshold limit, and all the methanogens are going to die. So there will be no production of energy, because you know that methane is energetic compound. It can be used as fuel as well. So there will be waste doing this anaerobic digestion. So calculate the maximum H2 partial pressure at which strain S can just gain some energy from catalyzing reaction 1 at pH 7 and 25 degrees Celsius by assuming that both ethanol and acetate are present at the concentration of 10 raised to power minus 6 mole. So all this scenario is there, but only this much information is required. For that purpose, we need to calculate the partial pressure of H2. This is 10 raised to power minus 6. You can use these values of Gibbs free of energy of formation. Okay, the major aim is to we want the first reaction to be feasible. So we want to reduce the Gibbs free energy of reaction to less than zero. Here the Gibbs free energy of reaction is positive, so we need to remove some of the hydrogen, which can be done by the second reaction. So how much hydrogen is needed to be removed? What can be the partial pressure to make the first reaction negative? Okay, so under standard condition, all these values, acetic acid, acetate, H plus, H2O will be 1 and partial pressure of H2 will be 1 bar. So this reaction is ender organic, means Gibbs free energy of reaction is positive. In order to get negative Gibbs free energy, delta GR, the term RT has to be smaller than delta Gibbs free energy of change in Gibbs free energy of reaction. So this is how we'll solve it. RT should be less than 49.6, and if we multiply both sides by E, okay, anti-log of both sides, then this can be done by calculator. So we'll get Q less than 2 into 10 raised to power minus 9. Now we know Q, we can use the laws and we can find out the partial pressure. Please note this down. This was the last question. So PPT will be shared with you all. Also, this is my email ID. I'm typing in the chat box. So in case of any doubt, if you get in between these sessions, you can message me here. You can just go there and post your question, and I'll be happy to answer them. So that's all for today. I'll see you next week. You all can leave the session.